So what I want to cover is integration by parts, which you'll see in like a Calc 2 class. So here's the method. We know that the derivative of the product is going to be the product rule. So if we integrate both sides of this product rule, the integral of the derivative is just going to be the function f of x times g of x, and then the integral of the sum is going to be the sum of the integrals. Now what I want to do is I want to rearrange to be able to solve for this. So solving for this, we have, fg minus the integral of f prime g dx. Now, the integration by parts usually uses this notation. The integral of u dv is equal to uv minus the integral of v du, which is just a restatement of this thing, where this is u dv, and this is uv minus the integral of v du. Now, v du. So u is f of x, v is g of x, du is f prime of x dx, and then dv is g prime of x dx. So really, by parts is nothing more than a reorder of the product rule. It's almost like an inverse product rule. Now I'm going to do the method to integrate this. So what we want to do is we need to pick a u, and then we need to pick a dv. So u we want it to be differentiable, and dv we want it to be integrable. So I'm going to say u is equal to x, and dv is equal to the cosine of x dx. So your u being one of the functions, so being this function, and then your dv is going to be the other function combined with its differential. So now what I'm going to do is I have to find du, and then I also have to find v, and I'm going to pop it into this equation to be able to integrate. So du or du dx would just be 1. So du dx, of course, would be 1. So send the differential to the other side. Du is just going to be 1 dx. So just dx. And now I have to integrate the cosine of x. So v, the integral of the cosine of x, is going to be equal to the sine of x. Now we know the formula for my parts is uv minus the integral of v du. That's going to be the integral of this. This is of the form. This is of the form the integral of u dv, which is going to equal this, u dv. Now uv x times the sine of x minus the integral of v du. So this is going to be the sine of x dx. And our goal is, even though that this integral still has another integral in here, that this side is integrable, or at least simpler, so I can maybe possibly do it again. So now the integral of the sine is going to be minus cosine, so this is going to be the sine of x minus cosine of x plus c, so this is going to be x sine of x plus cosine of x plus c. So next I'm going to want to integrate this. So what we're going to have to pick is we're going to have to pick a u and then a dv. Remember that one of these functions I want it to be integrable, and the other function I want it to be differentiable. So I know that the natural log function I can differentiate, and the x cubed dx function, this x cubed I can integrate. So the derivative of natural log of x is going to be equal to 1 over x, and the antiderivative of x cubed is going to be x to the 4th over 4. So now we know it's going to be equal to uv minus the integral of v du. So this will be equal to uv. So I'm going to write the polynomial first, natural log of x, minus the integral of v du. So this is going to be x to the 4th over 4. Multiplied by 1 over x. Oh, forgot the differential dx. So remember that your du's and dv's need to be combined with your differentials. So I'm going to simplify this, and it looks like that thing's integrable now. So this is going to be x to the 4th over 4, natural log of x, minus the integral of, I'm going to pull out the constant, minus 1/4 the integral of x cubed dx. Now I can integrate this, since this is nothing more than a polynomial, so this is going to be x to the 4th over 4, natural log of x, minus 1/4 times x to the 4th over 4, plus c, so this will become x to the 4th over 16. So pause it, and I'm going to set up another one. So what I'm going to do is I'm going to integrate the natural log of x dx. And when I had this previous problem, sometimes students want to put the natural log of x over here because they think they can integrate it, but it's not really easily integrable without the by parts method. So what we need again is we need a u, and then we need a du. So I need a function I can integrate, which is going to be the natural log of x. And then that means du is going to be the only function left over, and really there's just a multiplication of 1 here, so this is just going to be a 1 dx. So integrating u, so du is going to be 1 over x dx, so forget your differential, and differentiating natural log of x, and integrating this, so this means u is going to be equal to x. Now when we set up our by parts, we have uv minus the integral of it's funny. So uv minus the integral of v du. So v times du. So this will simplify x natural log of x minus the integral of just dx. And this is going to be x natural log of x minus x plus c. So in order to integrate something that's is as simple as a natural log function, we need to do this by parts. So sometimes we have to run this method more than once. That this will simplify, but this piece right here might still be more complicated, and we might have to do a by parts method again on this. You might have to do this over and over and over again. So I'll set up a one where we have to repeat this process more than once. So this integral, what I have is I have a multiplication of a polynomial and then an exponential function. So we have to pick a u and then a dv. So u being differentiable, dv being integrable. So a lot of times what I want for u is I prefer your du to get easier and this to just be possible. So I want this to, this function, I'm choosing the polynomial because I know when I take the derivative of the polynomial that the second degree polynomial is going to turn into a first degree polynomial. So this kind of reduces, and then I'm picking my e to the r dr because this is just easily integrable. So now we know that this integral is going to be uv minus the integral of v du, so 2 to the r plus 1 times e to the r dr. Forget that differential. Now, notice that this is still not integrable as it sits, but before we had a second degree times that exponential, now we have a first degree times that exponential. So what we can do is we can just run this process again and see what happens here. So I have u being equal to, I'm going to pick the polynomial again, and dv is going to be equal to e to the r dr. So that means du is going to be equal to just 2 the r, and v is going to be equal to e to the r. So don't forget, we still have this piece. So I'm going to have r squared plus r plus 1 e to the r minus, whatever this gives us. So this is going to be uv minus the integral of v du. So this is going to be 2 e to the r dr. And now this is integrable as it sits. I don't have to run the by parts method again. So this is going to be r squared plus r plus 1 e to the r minus, don't forget I'm going to distribute to here, so this is going to be minus 2 to the r plus 1 e to the r. And this is going to be minus and a minus, so this will be plus the integral of this thing. And the integral of this is just going to be 2 e to the r plus c, so 2 e to the r plus c. Now, you might, when you get to this part, you might have to run it again, and then again, and then again. In the next video, I'll do a tabular integration tool where we can do this method really quickly, but it's very specific to the functions you have here. So that'll be in another video. Now, another cool method for the by parts is what's called a repeated integral. And I'll set it up and then you can see it in practice. All right, so this will end up being a repeated integral, and here's kind of the reason why. When I set up my u and I set up my dv, I tend to make my dv's my exponential functions when I can, because they're really easy to integrate. And then my u's are going to be my cosine function. But there are sometimes it matters and sometimes it doesn't. There's sometimes when you can switch these and it'll still work, but there are other times we can't. And you'll know it'll get more complicated. The second part of the integral will get more complicated. So then u is going to be equal to, well, the derivative of the cosine of 3x is going to be equal to minus the sine of 3x multiplied by the derivative of what's inside, which is going to be 3, my differential. And then v is going to be equal to e to the x. So this integral here is going to be uv, so e to the x cosine of 3x minus the integral of v du. So this would be minus 3 e to the x sine of 3x dx. I put this as far as a coefficient because I don't like to put it after the sine function. I need to make sure it's not part of the argument of the angle of the sine. Now, minus and minus, this would be plus. And I'm gonna have to write it again. We can see that it's something very similar. So let's pull out the 3 as well. 3 integral. So integrating this again, we have u is equal to the sine of 3x. So that means du is going to be equal to 3 cosine of 3x dx. And then my dv is going to be equal to e to the x dx. And then by running through this again, don't forget my first piece, e to the x cosine of 3x plus 3 times, well, your by parts. So u times v, so e to the x sine 3x minus the integral of v du. So I'm going to put that e there again. So 3 e to the x cosine 3x dx. And taking the 3 and putting it out here as well because it's a constant. So minus 3 times the integral of e to the x dx. I'm going to expand this 3 so we have e to the x cosine 3x plus 3e to the x sine 3x. 3 times negative 3 is minus 9 times the integral of e to the x cosine of 3x dx. And this is really the beauty of this repeated integral is remember that we were trying to integrate this, the integral of e to the x cosine of 3x. And guess what we got back? We have that integral back. So if this side is also that integral, then what I can do is I can move this integral to the other side. I can add this 9 to this side because this is the left side of that equation. And so adding that over, I'm going to have 10 times the integral of e to the x cosine of 3x dx is equal to, well, what's left over here is going to be e to the x cosine 3x plus 3e to the x sine 3x. Now, my job is to evaluate this particular integral right here, the integral of e to the x cosine 3x. So I'm going to take this 10 and divide it to the other side. So the integral of e to the x cosine 3x dx is going to be this side of the equation divided by 10. So e to the x cosine 3x plus 3 e to the x sine 3x all divided by 10. And remember that you still have your plus c's.